In this lesson, we're going to focus on galvanic cells. So what exactly is a galvanic cell? A galvanic cell is basically a battery. A battery is a device that can convert chemical energy into electrical energy. So let's say if you connect a battery to a light bulb, there's a chemical reaction that's occurring in the battery, and that's going to be converted to electrical energy. This is the positive terminal of the battery, and this is the negative terminal of the battery. So electrons will flow from the negative terminal through the wire and back towards the positive terminal. And whenever electrons move through a wire, you have a current flow. And the flow of charge can be used to turn on the light bulb or to do work. You can cause the motor to spin. And that's basically what electricity is, just moving electrons. And so a galvanic cell is basically a battery. Every time you use a battery to power your laptop, your cell phone, or even a calculator, the battery inside of it is using chemical energy and converting it into electrical energy to do useful work. And so let's talk about the operation of a galvanic cell. A typical galvanic cell is composed of two half cells. So I'm going to draw two beakers, and each beaker is going to contain an electrode. An electrode is simply a metal. Metals conduct electricity. Now, the metals have to be in contact with a solution. So this is going to be a zinc metal, and this is going to be copper metal. So that's the copper electrode. The half cell on the left is going to contain a solution of zinc sulfate, and for the one on the right, it's going to contain a solution of copper sulfate. Now I'm going to connect each electrode to a wire and to a light bulb, or you could use a meter if you want. Now we also need a salt bridge to prevent the buildup of charge between these two solutions. Now let's talk about what's going to happen. Copper has a very strong tendency to accept or acquire electrons. Zinc wants to give it away. So zinc is going to lose 2 electrons per atom. And so it's going to turn into the +2 or the 2+ ion. Now whenever a metal loses electrons, it's undergoing oxidation. And you need to know that oxidation always occurs at the anode. So zinc is the anode. The other electrode has to be the cathode. Reduction occurs at the cathode. So remember, oxidation is the loss of electrons, and reduction is the gain of electrons. So at the cathode, copper ions will acquire electrons to turn into copper metal. So if you look at the oxidation states, the oxidation state of any pure element in its natural state is 0. So for zinc, the oxidation state increases from 0 to +2, or 2+. So anytime the oxidation number increases, the substance is undergoing oxidation. It's losing electrons. In the case of copper, notice that it goes from +2 to 0. So the copper 2+ ion is being reduced because the oxidation number is decreasing. It's acquiring electrons. So these two reactions are known as half reactions. And you can easily tell if a half reaction is an oxidation reaction or if it's a reduction reaction. And here's how you tell. Look at the electrons, specifically where they are relative to the arrow. If the electrons are on the right side, you have an oxidation reaction. If the electrons are on the left side, you have a reduction reaction. And so that's a quick and simple way to determine if a half reaction is a reduction reaction or an oxidation reaction. But keep this in mind, oxidation always occurs at the anode and reduction occurs at the cathode. Now we know that zinc is giving away electrons. So electrons will always flow from the anode towards the cathode. So because the electrons are leaving the anode is negatively charged. Electrons always leave the negative terminal of a battery and flow towards the positive terminal of a battery. So the cathode has to be positively charged because the electrons are flowing to it. Now, as electrons flow through the light bulb is going to light up, provided if this battery has enough energy to light up the light bulb. Now, what's happening at the interface between the electrode and the solution, specifically the anode? Now, as the zinc atoms lose electrons, they turn into zinc ions. So let's say this is a zinc atom here. It's hard to see it, but let me just redraw it like this. So when that zinc atom gives up 2 electrons, it's going to turn into an ion. And so it leaves the electrode and it dissolves in a solution. Now, on the other side, there's already copper ions in a solution. So a copper 2 plus ion is going to be attracted to the incoming electrons because opposite charges attract. As the electrons flow on this metal into the solution, well, they don't really flow into the solution, but they're flowing through the metal in the direction of the solution. These copper 2 plus ions, they're attracted to the negatively charged electrons. And so they're going to accelerate towards that electrode. And as they accelerate towards the cathode, they're going to pick up the electrons at the interface between the cathode and the solution. And so as these ions acquire electrons, they turn into copper metal. And so they deposit themselves on the surface of the cathode. So over time, you'll notice that the cathode is going to get bigger because the copper ions are turning into copper atoms on the surface of the copper electrode. Now the zinc electrode is going to get smaller because it's losing mass. So in a galvanic cell, the anode, it loses mass. The cathode gains mass. So as electrons flow from anode to cathode, the anode is going to lose mass and the cathode is going to gain mass. Make sure you understand that. So this electrode is going to slowly disappear, and this one is just going to get bigger. And that's the basic principle for electroplating. You can transfer mass from one electrode to another electrode, but we'll talk about that in another video. Now there's another element that we need to talk about, and that is the salt bridge. What do you think is the purpose of the salt bridge? Why do we need it? Without the salt bridge, current will flow only for a very short time. You're going to have some electrons flow from the anode to the cathode, but as electrons flow towards the cathode, this side is going to have a buildup of negative charge, and this side is going to have a buildup of positive charge because it lost electrons. And so once you have that charge buildup, electrons will no longer flow, because once this side becomes positively charged, the electrons that went this way is now attracted to this side, and so it's going to reach a state of equilibrium. And so without the salt bridge, you won't have a constant flow of electricity. It's going to be very short-lived. And so the purpose of the salt bridge is to keep the solutions neutral. So as electrons flow from anode to cathode, this solution becomes negatively charged. This becomes positively charged. So to relieve the positively charged nature of this solution, what happens is the anions, which are known as positively charged ions, they're going to flow through the salt bridge to the other solution. So the zinc cations are going to flow towards the cathode. Cations, cathode, makes sense? The anions flows toward the anodes. Now this works in such a way that the two solutions remain neutral. But keep that in mind, anions flow towards the anode. Anions are negatively charged particles, and cations flow towards the cathode. And so that's how the salt bridge will prevent a buildup of charge. So now that we've discussed the basic operation of a galvanic cell and how it works, Let's talk about the cell potential and how to calculate it for this overall reaction. So we saw that zinc turns into the zinc 2 plus ion by giving up 2 electrons. Now the cell potential for this half reaction is positive 0.76 volts. And so this occurs at the anode. I'm going to write A for anode. And so that's the oxidation half reaction. So remember, anytime you see the electrons on the right side, it's oxidation. If the electrons are on the left side, it's reduction. Now the other half reaction, the copper 2 plus ions acquire electrons and turn into copper metal. And the cell potential for this half reaction is positive 0.34 volts. So this occurs at the cathode, and reduction always occurs at the cathode. So anytime you see the electrons on the left side of a half reaction, you know it's associated with a reduction half reaction. So what we can do is add up these two half reactions. Notice that we have 2 electrons on the left and 2 electrons on the right, and they will cancel. So on the left of the arrow, we have zinc and copper 2 plus. So this is going to be zinc plus copper. And on the right side, we have copper and zinc 2 plus. So zinc is a metal, so it's in a solid state. And on the right side, copper is a metal. Now the ions are dissolved in water, so they're in the aqueous state. Now to calculate the cell potential for this overall reaction, all we need to do is add up these values. So 0.76 plus 0.34 gives us an overall cell potential of 1.1. The cell potential looks like this. So it's 1.1 volts. Now we can represent the cell using a line notation or cell notation. So first you need to write the anode, which is zinc, and then use a single vertical line to separate the phases because these two phases are different. So in a solution we have the zinc 2 plus ion, that's in the first compartment on the left. And then you need a double arrow to separate the anode half cell from the cathode half cell, or you could say the oxidation half cell from the reduction half cell. So on the left side, this is for oxidation, which is associated with the anode, and the right side will be associated with reduction, which is with the cathode. So in the reduction half cell, we have the copper 2 plus ion dissolved in a solution, and we need to separate that because the electrode is in a different phase than the copper 2 plus ion, and so the cathode is copper metal, the anode is zinc metal. So that's a simple way in which you could represent this cell using cell notation, or also known as line notation. By the way, a galvanic cell is also known as a voltaic cell, so just keep that in mind. Now let's talk about the cell potential, also known as EMF, electromotive force. This is measured in units of volts, or you could describe it as a voltage. 1 volt is equal to 1 joule per coulomb. So what does this mean? When 1 coulomb of charge passes through a potential difference of 1 volt, it can do 1 joule of work. Joules is the unit of energy. It's also the unit of work. Work is basically the transfer of energy. And 1 coulomb is the unit of charge, or electric charge. Charge is proportional to the number of charged particles. The more electrons you have, the more charge that's flowing through a conductor. And so a volt represents the ratio between energy and charge. You could also say it's the work that can be done per unit charge. So that's how you can describe a volt, in case you wanted to know what it is. So you need to be familiar with voltage and current. Voltage is the potential difference between 2 points. Electric potential is measured in volts, and voltage is the difference between the potential of 2 points. For instance, let's say if you have a conductor, And let's say this is point A and point B. At point A, let's say the electric potential is 11 volts. And at point B, the electric potential is 10 volts. The voltage is the potential difference between these 2 points. So the voltage is 1 volt. So if we have 1 coulomb of charge, so 1 coulomb of electrons, and they're going to flow from a low potential to a high potential. So this would be positively charged because it exists at a high potential, and relative to the other one, this is negatively charged. So electrons will flow towards the higher potential, towards the positive terminal. And so if 1 coulomb of electrons flow from B to A, and it flows through a potential difference of 1 volt, as it goes from B to A, it can do 1 joule of work. So make sure you understand that. So voltage is the difference between 2 electric potential values. So both electric potential and voltage have the same units, volts. Now you need to be familiar with electric current. Electric current, which is represented by the symbol I, is the rate at which charge is transferred. So Q represents the electric charge in units of coulombs. Current is measured in amps. So 1 amp is equal to 1 coulomb per second. So if we have a current of 10 amps, that means that 10 coulombs of charge is flowing through every second. Or we could say that 20 coulombs of charge flows every 2 seconds. So 10 amps mean that every second 10 coulombs of charge passes through a given point. So charge is the current multiplied by the time. So make sure you know these values. So 1 coulomb is equal to 1 amp times 1 second. And 1 volt is equal to 1 joule per 1 coulomb. Now let's go back and talk about cell potential. The cell potential is positive whenever you have a spontaneous reaction. So that means that delta G is equal to a negative value. The cell potential is 0 when the system is in equilibrium. And so when the cell potential is 0, delta G is also equal to 0. And when the cell potential is negative, that means that you have a non-spontaneous process. And so delta G is positive. Now what you need to know is for a galvanic cell or a voltaic cell, the cell potential has to be positive. It can't be negative, because galvanic cells, they convert chemical energy into electrical energy. You can't derive energy from a non-spontaneous process. So the lowest that a galvanic cell can be is 0. So let's say if we have a cell potential, like the example that we had earlier, which is 1.1 volts. In this case, the battery is fully charged. It has energy to give away. It can power a laptop, or maybe not that much, but power a small light bulb. Now, as you use up the battery's energy, the voltage or the cell potential will decrease. And so over time, the cell potential will gradually get lower and lower. It's going to be 1.0 volts, 0.9, 0.8, 0.7. Eventually, it's going to reach a state of equilibrium while the cell potential is 0. At this case, it's fully discharged. So basically, the battery is dead at this point. That's when you throw it away and you buy a new battery. So make sure you understand that when the cell potential is positive, the battery or the galvanic cell has the ability to do work. It can power a light bulb, it can spin a small motor or something. But as you use up the battery's energy, the cell potential will gradually decrease to 0. Once it's 0, the battery is in equilibrium. It has no desire to react. It doesn't have any energy to release. And so at this point, the battery is considered dead. It can't do anything at that point. Now, to go back this way is a non-spontaneous process. However, you can charge up the battery by putting energy into it, by driving electricity into the system, so you can reverse the whole process. So you can drive a non-spontaneous process forward by putting energy into the system. But once you do that, it's no longer a galvanic cell, but it's an electrolytic cell. So for galvanic cells, the cell potential can be 0 or positive. For electrolytic cells, it could be anything. It could be negative, it could be positive, it could be 0. But the key difference is this. In an electrolytic cell, you need to put energy into it to make it work. For a galvanic cell, it generates its own energy. It converts chemical energy into electrical energy, so a galvanic cell can never have a negative cell potential. But for electrolytic cells, it can. Now let's talk about the construction of a galvanic cell. Let's say if we want to increase the voltage, how can we do so? Well, if you have two D-size batteries or two AA batteries, if you want to increase the voltage, you need to take the positive terminal of the battery and connect it to the negative terminal of another battery. And so this is the positive terminal of the second battery, and this is the negative terminal of the first battery. And each battery, let's say it's 1.5 volts. So when you connect it in series like this, and let's say you connect it to a voltmeter, the voltmeter is going to read 3 volts. And so you can increase the voltage of multiple batteries if you connect them like this. So let's say if you have 3 batteries, that is 3 1.5 volt batteries connected in series, then the total voltage is simply the sum of the individual voltages of these 3 batteries. So 1.5 times 3 is 4.5. So that's what the voltmeter is going to read if you connect 3 batteries in series. Now let's apply this to the galvanic cell. So let's say this is one compartment, here's the other one, and let's say this is the salt bridge. Here's the zinc electrode, and here is the copper electrode. And then we have a solution inside. Now we said that the copper electrode in this example was the positive terminal, and the zinc was the negative terminal. And so this cell will produce a voltage of 1.1 volts. Now let's draw another cell right next to it. So we still have the same salt bridge. Here's the zinc electrode, and this is going to be the copper electrode. So what we need to do is connect the negative terminal of the second battery to the positive terminal of the first battery. And so let's say if we connect the voltmeter across these 2 points. Now it's no longer going to read 1.1 volts, but rather it's going to read the sum of these 2 values. So it's going to read 2.2 volts. And so as you connect a galvanic cell in series with another galvanic cell, you have to take the positive terminal of one galvanic cell connected to the negative terminal of the other, and then the other 2 remaining terminals or electrodes you connect into the voltmeter. If you do that, the voltage will increase proportionally. So if you connect 3 galvanic cells together, it can be 1.1 times 3 or 3.3 volts. And so that's how you can make batteries with higher voltages. That's how you can make a 12 volt battery or a 9 volt battery, is by connecting smaller batteries in series with each other until you get your desired voltage. Now what about increasing the current delivered by a battery? How can we increase the current? To increase the current, you need to increase the size of the electrode. That is, you need to increase the surface area. So for example, let's say this is the top view of the zinc electrode. And let's use this as another zinc electrode. The zinc electrode on the right has more surface area than the one on the left. As a result, a battery that uses this electrode will deliver more current, measured in amps, that will flow through the circuit. And so if you can increase the surface area of the electrodes, what happens is you decrease the internal resistance of the battery, and so the current delivered by the battery, that goes up. Now if you have a metal electrode, it may not be practical to increase the area of that. So what some batteries have is, instead of having just a metallic electrode, sometimes the electrode can be pressurized into a powdered form. So let's say if you use a powdered form of zinc or a powdered form of graphite as an electrode and you pressurize it, you can get a lot more surface area doing it that way. And so you can get a battery that can deliver a high current. So the goal is to increase the surface area of the electrode. If you can do that, then you can increase the interface between the electrode and the solution. So the greater the contact area between the electrode and the solution is, the more current that can be delivered by that battery. So that's how you can increase the current of a battery, is by increasing the surface area of the electrode. Now let's say if you have two batteries. If you connect them in series, you can increase the voltage. But if you have two separate batteries, and if you connect them parallel to each other, you can increase the current. So for example, let's say if you have a short circuit in this battery, which is not always the safest thing, but let's just talk about it. When you have a short circuit, it can deliver a lot of current. So let's say this battery can release 10 amps of current. Now keep this in mind, electrons flow from negative to positive, but conventional current is defined as the flow of positive charge. So conventional current flows from the positive terminal to the negative terminal, but electrons flow from the negative terminal to the positive terminal. So if this battery on its own can produce a current of 10 amps, now let's say if you connect it in series with another battery, and let's say that these two batteries are identical, and you create a short circuit, you can get a current of 20 amps. This will still deliver 10 amps of current, and this will deliver 10 amps of conventional current. So the total current flowing in this branch will be 20 amps. So if you connect two batteries parallel to each other, you can increase the current that they deliver to a circuit. Now keep in mind the electrons are flowing in the opposite direction, from negative to positive.